Hello everybody, welcome into another lesson. So today we are going to do some coordinate geometry proofs. This is piggybacking off of yesterday's lesson where we did coordinate geometry problems. Today we're going to do some proofs with them. So our very first problem is, what kind of figure is quadrilateral OQRS? As you see, we definitely have a quadrilateral here where you have O, vertex O, with at the origin at the point 0, 0. You have Q, vertex Q, at the point 0A. You have vertex R at the point AA. And then you have S at the point A0. So we need to figure out what kind of quadrilateral is OQRS. So looking at this, it could be a parallelogram, it could be a rhombus, it could be a rectangle, it could be a square. So what we need to determine is which one of those is it. First thing I would do is determine the slope of two lines. The reason I say that is, if we can determine the slope of two of these lines and determine that two of these lines are perpendicular to each other, we can determine that at minimum this is a rectangle. You know why? Because there is that part of the theorem that goes all the way back to when we were talking about quadrilaterals that states if one angle of a quadrilateral is a right angle, then the quadrilateral is a rectangle. That's quite a throwback to way earlier in the course, but why don't we do the slope of QR? So I'm going to find the slope of QR here. Okay, so the slope of QR will take, of course, that's your y2 of A minus your y1 of A all over your x2 of A minus your x1 of 0, which would give you 0 over A. So that means the slope of QR is equal to 0. So what does it mean to have a 0 slope? It's a horizontal line. It's a flat horizontal line. Well, that's great. Now, why don't we take one of these lines adjoining it? Oh, let's go with OQ. Why don't we take the slope of OQ? Whoops. Let's find the slope of side OQ. Well, we'll take that y2 of A minus the y1 of 0 all over the x2 of 0 minus the x1 of 0, which would end up giving you A over 0, which would mean this is an undefined slope. Okay, so we have an undefined slope. What does an undefined slope mean? An undefined slope is a straight vertical line. And in a sense, you could argue that an undefined, like if you have a denominator of 0 for one of the slopes and you just have a 0 for the other slope, you can argue that they're reciprocals or even negative reciprocals, since you can make 0 the negative reciprocal, right? Because 0 is neither positive nor negative. If you throw a negative sign on the 0, it's still going to be 0. So, and we can also geometrically see that when a straight horizontal line and a straight vertical line meet, they are perpendicular. So we can actually now confirm that this quadrilateral OQRS is at minimum a rectangle. This is minimally a rectangle. Now, here's the other side of this. Is it a rectangle or a square? Because we've narrowed down it's a rectangle, but it could also be a square. Well, how are we going to check to see if it's a square? If you have a quadrilateral that's a rectangle with two consecutive sides that are congruent to each other, then it's a square. So in other words, you're going to want to find the distance from points to find the length of each side. So why don't we find the distance from Q to R? Well, that's going to, of course, be your x2 of A minus your x1 of 0 to the second power plus your y2 of A minus your y1 of A to the second power. Okay, so A minus 0 is just A. You get the square root of A squared. And then you have A minus A is 0. Well, 0 squared is just 0. So you have the square root of A squared, which would just give you a length of A for QR. Now, what if we want to find RS? That's the next consecutive side to this quadrilateral. So RS, we'll take, of course, our distance formula. We'll take the x2 of A minus the y2 of A. I'm sorry, minus the x1 of A. So you'd have A minus A squared plus you have your y2 of 0 minus your y1 of A squared. Which, of course, would give you, what's A minus A? It's 0. 0 squared is 0. We don't even have to worry about that. What is negative A to the second power? Well, that's just A squared. So you get the square root of A squared, which equals A. So we can now use the fact that this quadrilateral is a rectangle and the fact that we have two consecutive sides that are congruent to each other. So what kind of quadrilateral is OQRS? It's a square. We have determined then by those two factors that quadrilateral OQRS is a square. And we can demonstrate that by slopes and by side lengths. Okay, now we're going to keep this rectangle up because there's some other facets to this here. There's some other exercises I would like to do with it. Alright, so what is the next part to this? Show that segment OR is congruent to segment QS. Alright, so we want to show that segment OR is congruent to segment QS. Well, we want to show this, right? Using coordinate geometry. From regular geometry, we already know that the rectangles of a square are congruent. We just got to prove that they're congruent. That the diagonals of a square are congruent. We just have to prove that they're congruent using coordinate geometry. So if it helps, what I'm going to suggest here is that we draw our diagonals from O to R and then from Q to S. We will have our diagonals, okay? So let's start with the distance from O to R. Why don't we find OR? That, of course, is equal to the square root of what is your second x from O to R. Your second x would, of course, be A minus your first x of 0. That'd be squared. Plus, then you have your second y coordinate, which is also A, minus your first y coordinate of 0, which would be squared. So this is going to give you, of course, the square root of A squared plus A squared, which would give you the square root of 2A squared. Alright. Which means that OR has a length of A times the square root of 2. So OR would have a length of A times the square root of 2. Now we need to hope that QS has the same length. Let's deal with QS. Again, do your distance formula. From Q to S, your second x-coordinate is A, minus your first x-coordinate of 0. That would be to the second power. Plus, then you have your second y-coordinate of 0, minus your first y-coordinate of A to the second power, which would give you, of course, what's A minus 0? That's just A. So that would give you A squared. Plus, then you have 0 minus A, which is negative A. Negative A to the second power, that's positive. That turns into positive A to the second power, which would give you the square root of 2A squared, which therefore means that the length of QS is equal to A times the square root of 2. Therefore, we have now proven that OR is congruent to QS. Simply by using the distance formula, we can prove that the two diagonals are in fact congruent to each other. All right. So as a matter of fact, why don't we keep these distances in our back pocket? Let's write them over here. That OR is congruent. No, let's write it as a distance. OR equals QS, which equals A times the square root of 2. So we got the lengths of each of these diagonals now. Now we're going to go on to prove something else, because the exercise after this is going to come in. These lengths are going to come in handy. All right. Show that segment OR is perpendicular to segment QS. We need to show that segment OR is perpendicular to segment QS, which are the diagonals. Show that the diagonals are perpendicular to each other. Well, if we remember all the way back to when we were studying quadrilaterals, the diagonals of a rhombus are perpendicular to each other. And a square, by extension, is also a rhombus, but it's a special type of rhombus where it's all right angles. So if a square is a rhombus, that means the diagonals of the square will also be perpendicular to each other. So we need to take the slopes of each of these diagonals and then show that they're perpendicular. So let's take the slope of OR. So the slope of OR, that's going to equal your y2 of A minus your y1 of 0 all over your x2 of A minus your x2 of minus your x1 of 0, which would give you A over A, which would give you 1. So the slope of diagonal OR is 1. Now let's find the slope of QS. So the slope of QS, take your x2, your y2, which would be 0, minus the y1 of A, all over your x2 of A, minus your x1 of 0, which would end up giving you negative A over A, which gives you a slope of negative 1. And we know that when we multiply these two slopes, we'll get negative 1, which is exactly what you should get if they're perpendicular. So we can say that the slope of segment OR times the slope of segment QS equals -1. Therefore, segments OR and QS are perpendicular to each other. So since their slopes, the product of their slopes equals -1, therefore diagonal OR is perpendicular to diagonal QS. That's what enables us to say that. Alright, one more thing we got to prove with this, then we move on to a trapezoid example. Alright. What are we out to prove here? Show that this time we want to show that diagonal OR bisects diagonal QS. Well, in general, we know that the diagonals of a parallelogram bisect each other back when we studied quadrilaterals. That much is true. However, we're in coordinate geometry. We want to show that these diagonals bisect each other. Well, okay, so here's something. If, which this is a quadrilateral, these diagonals bisect each other, what does that mean? That means that the diagonals will meet at the midpoint of each of the diagonals. So we need to find the coordinate of the midpoint here in the middle. This is going to come into play. I'm going to call this coordinate point M for the midpoint. That might help us. Now, if you want to find M, that is going to, of course, you're going to want to use your midpoint formula. So you'll take your first x-coordinate of 0 plus your second x-coordinate of A, divide that by 2, then take your second y-coordinate of A, your first y-coordinate of A plus your second y-coordinate of 0, divide that by 2, which gives you that point M is located at the point A over 2, A over 2. Alright, so let's put that here. M is at A over 2, A over 2. So we found now the coordinate of the midpoint of the diagonals, which is going to be very helpful. So I kept these lengths up here for a reason. Each diagonal, the whole diagonal from O to R and then from Q to S, both equal A times the square root of 2. If they're bisected, you should get a length of half A times the square root of 2 for each. Right? So let's go from Q to M here. Let's start on diagonal QS. Let's find the distance from Q to M. So the distance from Q to M would equal, of course, your x2 of A over 2 minus your x1 of 0 raised to the second power plus your y2 of A over 2 minus A raised to the second power. So then we continue here with our distance formula. A over 2 minus 0, that's just A over 2 to the second power, which then plus you'll have A over 2 minus A. Well, A could be the same as 2A over 2, right? So if you did A over 2 minus 2A over 2, you would get negative A over 2 raised to the second power. Negative A over 2 would be raised to the second power, which would end up giving you the square root of a squared over 4 plus a squared over 4, which gives you what? Then you would have the square root of 2a squared all over, what's the square root of 4? That's 2. Which would end up giving you then, of course, a times the square root of 2 over 2. Which would show then that QM is literally half of QS. So let's place some congruency markers there. QM is half of QS. So you have a distance of a times the square root of 2 over 2. And then if you subtract that from the whole length of a times the square root of 2, you would get that MS is a times the square root of 2 over 2 for its distance. So we can show now that QM is congruent to MS, which helps. We can prove that that diagonal is bisected. Now, we also need to prove that the other diagonal is bisected. So let's prove that the other diagonal is bisected, okay? So let's do OR. So let's go find the distance of OM. Find the distance of OM. Of course, you'll take your x2, which would be, again, a over 2 minus 0 raised to the second power plus your y2 of a over 2 minus 0 raised to the second power, which then, of course, would give you, of course, a over 2 to the second power, which would turn into a squared over 4, plus another a squared over 4, which would, of course, give you the square root of 2a squared over 4, which separates into the square root of 2a squared over the square root of 4. Well, the square root of 4 is just 2, which, to simplify this, would end up giving you a times the square root of 2 all over 2. And if OR has a length of a times the square root of 2, and you subtract the length of OM here, you would find that the length of MR has the exact same length. So we could place congruency markers on those too. So now we have shown that OM is congruent to MR. Therefore, OR bisects QS. Since we have shown that each half of the diagonals are congruent to each other, we can therefore prove that OR bisects QS. Alright. That's it for this one. We have now some with trapezoids. We're going to work on some trapezoids here. Let me see what this one looks like. Okay. I know that's a bit different. This coordinate geometry stuff's a bit different, but it is very necessary to use in proofs. Coupling with what we've learned earlier in the course. Okay. Alright, so we have a trapezoid with those vertices there and those coordinates. So what are we aiming to do here? So prove that the median of the trapezoid is parallel to the bases. So we're going to start out proving that the median of the trapezoid is parallel to the bases. Well, I think it would help if we found where the median of the trapezoid is supposed to go, right? Why don't we draw the median of the trapezoid? The median of a trapezoid always goes from the midpoint of one leg to the midpoint of another leg, of the other leg of the trapezoid. So, if we were to find the midpoint of side ON, let's find midpoint of ON. What do we have? You're going to take your x1, which would be, of course, at 0, it's 0, 0 at point O. So 0 plus b all over 2. And then your y1 would be, of course, 0 plus your y2 of c all over 2. So the midpoint would end up being b over 2, c over 2. So that is therefore the midpoint of side ON. So why don't we call this point point Q? We'll call that point Q, which has the coordinate of b over 2, c over 2. Alright, and then we need to, of course, find the midpoint of MP. Let's find the midpoint of MP. Whoops, I didn't want to erase what that point actually was. I certainly didn't want to do that. Forgive me for that. Alright, so what is the midpoint of MP? Well, let's do the midpoint formula. So you'll take your x1 of D plus your x2 of A all over 2, and then we would have your y2 of C plus your y1 of C plus your y2 of 0 all over 2, which would then end up giving you, for your midpoint, you would have, I like to have these in alphabetical order. We'll say A plus D all over 2, and then C over 2 for the y coordinate, right? Okay, so now why don't we put the midpoint of MP here? We'll call this point R. It'll have the coordinate A plus D all over 2, and then it'll be C over 2 for the y coordinate. So now we found the coordinates of the midpoints of each of the legs, which will give us the median. Well, we want to prove that the trapezoid is parallel to the bases, right? What does it mean for the lines to be parallel to each other? That all their slopes have to equal each other, right? The slopes have to be equal in order for them to be parallel. So let's go ahead and find the slope of NM. We will find the slope of NM. So the slope of NM, of course, that's going to be your y2 of C minus your y1 of C all over your x2 of D minus your x1 of B. Well, that would just, C minus C is 0 over D minus B, which of course equals 0. So we have a 0 slope on NM. Now, of course, we need to find the slope of QR. So the slope of QR is going to be a little bit more fun because of the fractions. But find your y2 of C over 2 minus your y1 of also C over 2 all over your x2 of A plus D all over 2 minus your x1 of B over 2. Well, C over 2 minus C over 2 is just 0, and it doesn't matter what the heck these are in the denominator. The slope of QR would in turn also equal 0. So now we have proven that at least that NM and QR are parallel to each other, but is it parallel to OP? Let's prove that it's parallel to OP. So the slope of OP would equal, of course, your y2 of 0 minus your y1 of 0 all over your x2 of A minus your x1 of 0. Well, so you would end up with 0 over A, which would give you 0. So the way to word this now is that you would say the slope of NM equals the slope of QR, which equals the slope of OP. Therefore, since all these slopes are equal, we can say that QR is parallel to NM, which is also parallel to OP. We have just now proven that all three of these bases are parallel to each other, which is exactly what they were asking, by finding all these to have a slope of 0. Now here comes the fun one. Here's really going to be the fun one. We're going to keep the coordinates up. I have a reason for it. Why what the heck? I don't know why I do that sometimes. Alright. There we go. Alright. Now, what are we seeking to prove? Alright, so here's going to be a fun one. We want to prove that the median of the trapezoid equals the average of the lengths of its bases. If we remember earlier in the course when we talked about quadrilaterals and when we spent time on trapezoids, the median is equal to the average of the lengths of its bases. So it's going to be equal to half the sum of the length of the first base plus the length of the second base. It's equal to half that sum. So we want to show that the length of this median equals half the sum of the length of the two bases with coordinate geometry. Well, why don't we find NM? Let's start out with the length of NM. So, of course, we'll use your distance formula. Take your x2 of D minus your x1 of B, raise that to the second power, plus then you'll take your y2 of C minus your y1 of C raised to the second power. Well, C minus C is just what? That's 0. All we really have to worry about is the square root of D minus B squared, which would just give you D minus B. So the length of NM equals D minus B. So we found that. Now what is let's go with the length of OS. What is OS? Use your distance formula. That's going to be equal to, of course, the square root of, take your x2 of A minus your x1 of 0 squared plus your y2 of 0 minus your y1 of 0, raise that to the second power. 0 minus 0 is 0. We just have the square root of A squared, which would mean that OS has a length of A. Alright, before we go finding the length of QR, why don't we find the average of the sum of these two bases? So we will take half of NM plus OS, right? Half the sum of the two bases. That's going to equal half of D minus B plus A. Which in fact would give you, you could write this as A plus D minus B over 2. That's the average of the sum of the two bases, A plus D minus B over 2. Now, if this is really true, then QR should equal A plus D minus B over 2. Let's see if that's the case. QR, the distance for that, of course, is your, let's see, take your x2 of B minus 2, B over 2. Whoops, I'm sorry, I got that wrong here. 1 second. Your x2 would be A plus D over 2 minus your x1 of B over 2 raised to the second power plus then your y2 of C over 2 minus your y2, which is minus your y1, which is also C over 2 raised to the second power. Well, what would you have then? C over 2 minus C over 2, that's just 0. Forget about that. You'll end up with the square root of A plus D minus B all over 2 to the second power. The square root of that to the second power, which would, what do you know? It gives you a length of A plus D minus B all over 2. Therefore, you can say that the median is equal to the average of the lengths of its bases. We just proved that by taking the average of the length of the bases, then finding the length of QR. We just proved that this assertion was true. All right. I got two more to do here. It also concerns this particular trapezoid, but we're going to change it up a little bit. So yes, I know coordinate geometry is a lot, and I'm sorry about that, but this is very important for you. All right. Good news, though, we will not need the median. We're done with the median, at least. So we can get rid of the median of the trapezoid. That's not going to matter at this point for the next two exercises, but this trapezoid as a whole will stay up. So let's see here. We want to show that oh, wait a second. I forgot a very important part here. Assume A equals B plus D. So we will assume that A equals B plus D. So in fact, why don't we change the coordinate of S to B plus D 0? Right? We've gotten rid of A. We have just gotten rid of A. We are to assume that A equals B plus D. So there's your coordinate of S. Show that the trapezoid is isosceles. Alright, so we want to show that this in fact is an isosceles trapezoid. Well, what is an isosceles trapezoid? It's a trapezoid in which both of its legs are congruent to each other, right? So what does that mean? We need to find the distance between each one. So why don't we do ON? We'll start with ON. So find that distance, take your x2 of B minus your x1 of 0, raise that to the second power, plus take your y2 of C minus your y1 of 0 to the second power, which then would simply give you the square root of B squared plus C squared. That's all we can do for the distance, is that ON is equal to B squared plus C squared. Alright, so we found ON. Now we need to find SM. Let's find SM. Well, that's of course, take your distance formula, take your x2 of B plus D minus your x1 of D raised to the second power, plus then take your x2, take your y2 of 0 minus your minus your y1 to the second power, which would be C squared. Well, D minus D is 0, you just end up getting the square root of B squared plus C squared. So we just showed that ON and MS have the exact same length. So ON is congruent to MS, therefore this is an isosceles trapezoid. I'm abbreviating the trapezoid there. So since we showed the legs are congruent, this is an isosceles trapezoid. One last exercise, then we're done, I promise. Alright, now we want to show that the diagonals of this trapezoid are congruent. So do yourself a favor, draw your two diagonals. So let's draw the two diagonals of the trapezoid. We want to show that these diagonals are congruent. So let's find OM first. Let's find the length of diagonal OM. Well, of course, take your x2 of D minus your x1 of 0, raise that to the second power, plus take your y2 of C minus your y1 of 0, raised to the second power, which of course would just simplify into the square root of D squared plus C squared. Alright, now we need to find the length of NS. Find the length of diagonal NS, just take your distance formula. So you'll have the square root of x2, which would be B plus D, minus your x1 of B, raised to the second power, plus your y2 of 0, minus your y1 of C, raised to the second power. Well, B minus B is, that goes away. This would just simplify into the square root of D squared plus C squared once again. So we've shown that these two diagonals have the same length. We have shown that OM is congruent to NS. Therefore, diagonals are congruent. Alright? And it's almost like we just proved another theorem or something using coordinate geometry. We never touched on that diagonals of an isosceles trapezoid are congruent, but it's almost like we just used coordinate geometry to prove that. So we just discovered something very interesting. In fact, I'm sure there is a theorem for that out there, but it was never taught in this course until now. But that's it for this lesson. That's actually it for the coordinate geometry unit, kind of. The next lesson will start a 5-lesson series on transformations. We will talk about those. These will be shifting, reflecting, rotating, stuff like that. So I hope everyone has a great night and take care.